we're looking at this lemma on integration. If you have two partitions where one is contained in the other, I'll discuss exactly what that means. Then LF of the smaller partition is less than or equal to LF of this bigger partition, and similarly UF of the smaller partition is bigger than the UF of the bigger partition. Sorry, P is smaller, Q is bigger. And so the idea of the proof is this. I'm going to start with a partition. Here I have a function. I'll do the same for L and U. And I have a partition in red here. Now here's the basic idea of how to figure out the LF. Right? So I look at this interval right here. I look at these red lines P, partition it, and I'm just going to pick the smallest point of the function on the interval. So notice that this function is decreasing, so you always basically pick the rightmost endpoint. So, and then it looks like it goes to 0. So LF of P is just equal to the area underneath these purple rectangles. And similarly, UF, I do the same thing. I look at this interval, and I pick the highest point. Well, the highest point occurs right here. So this should look familiar from calculus. And I haven't begun to talk really about the lemma yet. Right, so now it's a decreasing function, so I can just take the left endpoint. Okay, that's fine. Now, these are lower sums, these are upper sums. That should be awfully familiar from calculus. The thing that changes things, though, is if I stick in, say, a couple extra points here. So Q is just P plus a couple extra points. So I'm going to throw in 2 extra points. And this is the part where we say, and maybe I'll put down, these will be green too. And I should also be really clear that the endpoints are also green. They should also be red as well. So maybe I'll fix that in just a second. So the endpoint should be part of the partition as well. So I'm just taking my red partition, and I'm just throwing in 2 extra points. And I'm going to see how this affects things. To do that, what color should I pick? I'll choose light blue. How does this change things? Well, notice this interval is exactly the same. So this rectangle is going to be exactly the same. Similarly with this part, right? The red and the green line up perfectly. The only difference is over here, where there was one partition, where there's kind of one interval, now I have 2 because that green line splits in 2. Similarly there. This is the lower one. So for the lower one, that means I'm just going to go up until I hit right there. And then this one's actually going to end up being the same. Notice what happened. Over here, the lower one, because I split this into 2 parts, the lower, if I pick the smaller value of this leftmost part, it goes above the original rectangle. And you can see that when you add points, when you add points, you get a bigger lower bound. And we'll see it even more so over here. Over here, look, this whole rectangle here, this purple rectangle is basically 0. But if I add this Q point, this green point right here, part of this rectangle is non-zero now. So when you add points, so essentially what's happening here is that this is the lowest point right there in this original interval. So the question is, how much of the real estate down here gets to use that lowest point? Well, if you have more things in your partition, the answer is less gets to use the lowest point here, which means that the thing off to the left here, this rectangle, has to use a bigger point, which means that you're going to get bigger. So very similarly over here, I'll just draw it in. It's the same thing. So these 2 rectangles are going to be exactly the same because I haven't changed anything. But now this one gets to use the exact same rectangle. But this one here, the rectangle is smaller. So I get a smaller partition. Similarly over here, this I get to go up to there, but now I only go up to there for that. So I get a smaller upper partition. That's the basic idea behind the proof.